Hi, everybody. Thank you for being here. It is my great honor and pleasure to introduce Onur Mutlu. Onur is a professor at computer science at ETH Zurich and also a faculty member at Carnegie Mellon University. I'll try to be brief, but his bio is huge, so I'll just want to highlight what I find most important here. So he's also an ACM and IEEE fellow and elected member for the Academy of Europe. His broader interests are in computer architecture, obviously, systems, hardware security, and bioinformatics. And his work has influenced not only researchers, other researchers, but also industry. And some of his ideas have been actually implemented in commercial microprocessors and memory systems and so on. So he received two bachelor degrees in computer engineering psychology from University of Ann Arbor, and then he moved to University of Texas, Austin to get his master's and PhD. Sorry about that. In addition to his academic positions, he also started the computer architecture research group at Microsoft Research in the second half of 2000. And he held various product and research positions in companies such as Intel, Advanced Micro Devices, VMware, and Google. So Onur is extremely prolific researcher, and his work has led to several best paper, top picks, and test of time recognitions in all the top computer systems and architecture conferences. So as a numbering result, he is in the Hall of Fame for all the flagship computer architecture conferences, ISCA, Micro, ASPLOS, and HPCA. Besides leading the Hall of Fame for ISCA by a huge margin, he is also in the top 2 in every other computer architecture conference. So his excellent research has, for his excellent research, he has received the prestigious Computer Architecture Technical Awards, both from IEEE and ACM, the Edward McCluskey Technical Achievement Award from IEEE, and the Sigurd Maurice Wilkes Award from ACM. So with that, I'll pass the floor to Onur to talk to us about memory-centric computing. Onur, thank you for being here.
Thank you very much, Dionysius, for the kind introduction, and thank you very much, Nectarios, and everyone for the invitation to deliver this talk. I would, of course, very much have preferred to be in person in Athens, which I wanted to visit for many, many years, but unfortunately, due to the pandemic, we couldn't come there for 2 years, even though Micro was supposed to be in Athens for 2 years. And hopefully we will change that this year and going forward. I will share my screen right now. Can you see it?
Yes.
Okay. Okay, thank you. So I will start the talk then. So as Dionysius mentioned, I'm going to talk about memory-centric computing. This is actually a quite long talk. I tried to shorten it to 30, 40 minutes. Let's see how it goes. But feel free to ask questions at any time. It's supposed to be an overview of how computing should be going, in my opinion. And also, I will give you some recent results in terms of processing in memory. And also, I will delve into issues like hardware security and memory technology scaling that's pushing us to do something different in our computing systems. So even though it's titled memory-centric computing, I'm going to talk a lot about issues in computing in general. But the major problem that we have today in our systems is computing is bottlenecked by data. And data is really key for many, many applications, especially important applications like machine learning, genomics. These workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And we're doing increasingly sophisticated things on data. And on top of this, data is increasing. We can generate much more data than we can process. And here are some example applications that we have been dealing with. They're growing. And as a result, the demands on memory and storage systems is growing. And data is becoming much more of a performance energy bottleneck. There are some other applications that we're actually exercising, or at least similar applications that we're actually exercising in this call right now: web browsing, inference engines, training engines, video playback and capturing engines. And they're also bottlenecked by data in terms of performance and energy. And here are some other applications that we may not be thinking of on a daily basis, but genomics is a system or workload that's growing significantly because the cost of genome sequencing is reducing greatly, much faster than the cost of a transistor has been reducing for more than a decade right now. As a result, we're able to sequence many, many genomes. And clearly, this has been very important for the understanding of pandemics, but there are many, many other use cases, clearly. Unfortunately, even though sequencing technologies have been very successful in generating a lot more data, our sequencing computational analysis techniques have not been as successful in terms of scaling. So the bottleneck in genome analysis today is how fast we can process, move, and perform on the data. As a result, data becomes a big performance energy bottleneck. I don't have a lot of time to talk about genome analysis, but we do a lot of work in this area, actually. And I'm quite interested in pushing the technology forward with better computing architectures. And if you look at devices, today, devices are very small today. These are like what you would call IoT devices. You can move these devices to anywhere. In fact, these were some of the devices that were shipped to China first in the pandemic. They're being used a lot right now to understand many, many things related to genomes, including the viral genomes. But the problem is these devices are great at sequencing, but they're not good at analyzing data. Imagine if you could actually give these devices to people and people could sequence genomes and understand, ask intelligent questions like, what do I need actually right now to become better? Or if you give this device to a doctor who can use it at a critical point to understand what kind of drug they should deliver to a patient within a minute or so, wouldn't that be great? So we can actually have a lot of interesting applications if you can enable computation capability where the data is generated. And that requires, I think, a rethinking of how we design computing systems today. So today, what is happening with these devices, they generate data in the field, and that data gets moved to data centers, for example, far away. If you generate data in Africa, you have to move the data to Europe or United States and process the data over there. So data actually causes a huge performance energy bottleneck. And as a result, you cannot make real-time decisions. It takes days and days to actually get intelligent decisions out of these devices' data. So if you're interested, I think this is fascinating, and we do a lot of work in this area. This is an overview paper that we wrote last year on this topic. And we actually do a lot of data-centric designs, for example, to accelerate approximate string matching, for example. This is one example over here. But I think the future is very interesting in applications like this because the devices are scaling. Unfortunately, our computational capability is not scaling very well. And this talk is about why our computational capability is not scaling very well. And if you're interested in further, we have a lot of lectures on this topic that I will also mention toward the end of this talk. But clearly, data is today overwhelming modern machines. It's overwhelming the storage and memory capability, the communication capability, and in the end, the computation capability. Even though you may have a great computation engine, because you're bottlenecked by storage and memory and communication, computation is actually getting wasted. Data also greatly impacts robustness, energy, performance, and cost, and also as well as security. And I will mention that in the initial parts of my talk to actually motivate why we should be doing more intelligent computation near data. So if you look at a computing system, fundamentally, it consists of three key components: computation, communication, storage, and memory. And if you look at the grand overview of computing, we've heavily optimized the computing units, and we mostly ignored communication and memory and storage units. I believe that needs to change, and we need to take a much more holistic approach to how we design computing systems. So if you look at a processor-centric design today, it kind of looks like this. This is an old picture that I drew actually for my first National Science Foundation proposal when I was at CMU. But if you look at this picture, computation is limited on a chip. Even though we know how to design computation units really well today, most of the system is dedicated to caches, interconnect, other caches, other interconnect, memory controllers, other caches, main memories, other interconnect, storage systems. So most of the system, more than 90% of the real estate of a single node today is dedicated to storing and moving data. Computation is a very little part of it. But the system is still bottlenecked by memory. This should, I think, immediately raise some concerns about how we're designing our systems and where the bottleneck is. And even though we're dedicating a lot of resources to this bottleneck, that resource is still a bottleneck. And as a result, data becomes a performance energy bottleneck in our systems. Here, to give you a data point, this is a study that we did with Google a few years ago. We spent about 1.5 years, 2 years actually on this project. And we analyzed a lot of workloads that I will mention later on also. On mobile workloads, more than 60% of the total system energy is spent on data movement, just moving the data from the processor and the memory system. So my axiom going forward and the rest of this talk will be that an intelligent architecture, if you want to design intelligent architectures, and we would like to, I think, because these architectures will be making decisions for ourselves, they will have intelligence in themselves, but are they designed to be intelligent? If you want them to be intelligent, I think they need to handle data well. The question, of course, is how do you handle data well? And I think there are three directions over here. One is we should ensure that data does not overwhelm the components, the system we design essentially, via intelligent algorithms that operate on little amounts of data potentially, or that reduce the data very quickly, via intelligent architectures that do not move the data a lot, and via whole system designs, more importantly, algorithm architecture devices co-designed together so that data does not become a bottleneck. This is for the first direction. We're going to spend a lot of time in this direction the rest of this talk. But let me give you the two other directions also. I think we also need to design systems that are fundamentally intelligent. What does this mean? Fundamentally intelligent systems basically make their decisions based on data. If the data is flowing through the system and metadata is also generated or flowing through the system, we can use this so that we can improve our decision making. But if you look at the architectures today that we design, fundamentally, they don't really improve, they don't really learn from the data. So let's take an example of a memory controller. The memory controller on the cell phone, for example, has been working for 6 years. And it's using exactly the same policy it was dictated to use by a hardware designer. And that hardware designer clearly didn't know exactly what was going on in the system and what applications I would be using in my system, for example. What would a self-optimizing system be? A memory controller would actually observe its decisions and its actions based on the interaction with the environment, and it would change its policy based on the interaction with the environment. It would learn basically based on its actions. This I would call fundamentally intelligent. And humans are like this. For example, we interact with the environment. We learn based on our actions. If I put my hand on a hot stove, I will learn that I shouldn't put my hand on a hot stove again. But the memory controller today is not doing that. So I believe we need to redesign the entire system stack today to actually make it fundamentally intelligent. I'm not going to talk about this going forward in this talk because we don't have time, but I think this is very important. And the third direction is I think we need to understand, exploit properties of different data. If you look at data today, data is actually very various. It has many, many characteristics. It has privacy characteristics, security characteristics, compressibility characteristics, locality characteristics, approximability characteristics, bandwidth and latency sensitivity characteristics, or performance characteristics as well. But these characteristics are actually not communicated to the underlying hardware as well as the system. And the system, as a result, doesn't know what decision to make and how it should focus its policies based on the characteristics of the data. All data is mostly treated exactly the same. But if we actually communicate these semantic characteristics of the data into the underlying system, we can actually make much better system-level decisions, both at the hardware, the software levels, and we can actually improve our systems a lot. I call this data-driven or data-aware architectures. And again, I don't have time to talk about this in detail, but I will mention that. So basically, if you look at corollaries based on what I discussed, architectures today are not good at dealing with data. They're basically processor-centric as opposed to data-centric. As a result, they're moving a lot of data across the system. And we're going to talk about that a lot in this talk. Second, architectures are not taking advantage of vast amounts of data and metadata that's flowing through the system. They're designed to make simple decisions, human-driven decisions, as opposed to data-driven decisions. Fundamentally, they're not learning from data. Architectures today also don't know and exploit different properties of different data. They're designed to treat all data as mostly the same. As a result, they make component-aware decisions based on, for example, the banks in the memory system or some other characteristics of the memory system or the interconnect, as opposed to the criticality of the data. For example, is this security critical? Should I be protecting this much more than some other data? Those are the data-aware decisions that we would like to get to. So again, as I mentioned, I'm going to focus especially on the data-centric or memory-centric part of it. But I believe data-driven and data-aware architectures are parts of the same puzzle, if you will. And memory-centric architectures also become better if they're data-driven and data-aware. So that's kind of the blueprint of fundamentally better architectures going into the future, in my opinion. But I think to be able to enable this, we really need to rethink the entire stack. And this will be also clear in the data-centric architecture that I will discuss. We really need to rethink not only just the architecture level, but algorithms, languages, system software, as well as underlying devices that we design our systems with. But I believe we can get there step by step. And hopefully in this talk, I will give you some examples of getting there step by step. So going forward, again, in this talk, my axiom will be that if you would like to achieve the highest energy efficiency and performance and other characteristics that we care about, like security, dependability, and reliability, we really must take an expanded view of architecture. Not just focus on a single layer, but cut across the layers, co-design across the hierarchy, algorithms to devices, and specialize our systems as much as possible within the design goals. And I have another view of thinking about this. This is, many of you may be familiar with Richard Feynman, who is a very famous physicist, American physicist, well, world physicist. But he actually coined the term of, I would say, nanotechnology early on, without naming it that way. But basically, he mentioned in this famous talk that there's plenty of room at the bottom in late 1950s, meaning that if we could actually understand how individual atoms behave, we could design much more powerful computing systems, as well as much more powerful systems that can change our lives, like synthetic biology, etc. And later, nanotechnology advocates actually made this talk famous. And I still believe that we have plenty of room at the bottom. We just need to discover new devices that can enable us to understand the atomic interactions and do better at the lower level. And again, you can read Wikipedia. He actually talked about denser computing circuitry, like things like swallowing the doctor. These smaller devices can enable us to have significant advances in medicine, for example. But this is true today, I believe. It's getting harder with existing technologies, but there are some technologies that we need to look at going into the future, like future non-volatile technologies in memory, and some other technologies like potentially quantum, as well as carbon nanotubes, etc. We need to push the boundaries at the bottom. There's also some people that argue that there's plenty of room at the top, and this is also kind of obvious, I would say. Clearly, if technology scaling is becoming a problem, there should be more to be done in the software architecture, algorithms, etc., so that we can harness better performance, better efficiency out of a single transistor, for example. But I don't believe that it's just at the top. So I think there's still a lot of opportunity at the top and the bottom. We just need to do the research to understand what opportunities exist and how can we tap into them. But more importantly, in my opinion, if you actually communicate well between and optimize across the top and the bottom, top of the computing stack and the bottom of the computing stack, you can get to a much better place. And I think this talk is really about communicating better between the top and the bottom so that we can take advantage of the underlying technology with algorithms and software at the top so that we can get to a much better place. So that's why I have this expanded view that I mentioned earlier. Sorry, the slides are going a bit faster than I intended to be. That's why we need to think across the stack. And I think data-centric, data-driven, and data-aware architectures can all be enabled by thinking across the stack. Okay, now let me jump into the data-centric or memory-centric part of this one. And even if you look at the data-centric part, we want multiple properties. If you think about what should a data-centric architecture look like, clearly we want to process data where it resides. We don't want to move the data a lot in the system. We want to enable low latency and low energy access to data as much as possible because data is very important. We want to enable low-cost data storage and processing. And we want to intelligently manage data. We want to have intelligent controllers handling different properties of data, robustness, security, cost, etc. I'm going to talk about this intelligent data management. I'm not going to touch into the second and third points, but there's a lot of research that's going on in the field on this topic as well. I'm going to talk about the first one especially, but I'm going to motivate it with the intelligent data management part a little bit. So let's jump into it. I call this processing data where it makes sense. Today, we're processing data only in the processor, in the computation units. It could be the CPU, GPU, FPGA. It doesn't matter. You have to move the data to there first. And that movement starts from the sensors or storage units or memory units or the interaction with the user. So right now, the data has to move to the processing unit. So why not actually? So the question is, does this make sense? And hopefully the answer will be, it doesn't make sense in today's systems. And can we do something better? And when I say where it makes sense, I say that we should really process data where it gets generated or where it resides, as much as it makes sense, of course. Sometimes it makes a lot of sense to move the data to a computing unit that has a lot of locality, or the data has a lot of locality that the computing unit can exploit. We should still keep that, of course. But we should enable other options so that we don't waste a lot of energy and performance in our systems, and the data gets processed in places where we could actually process it. Today, we don't have any option. We have to move the data to the processing unit. But this is an old idea, of course, right? This is not something we invented. Processing in or near memory is an old idea. These are some of the earlier papers. There are even earlier papers that look at analog computing that kind of mix memory and logic. But you can see some earlier papers that kind of clearly specify there's logic in memory. And this is a very famous paper for Harold Stone, for example, a logic in memory computer. And they advocated different reasons for doing this. For example, Harold Stone's argument was cost. If you want to make a less costly system, we should really merge logic and memory. And I think a lot of his predictions came true. But today we're in a different place. So clearly this is an idea that has been advocated for more than 50 years, and it has not panned out. Why do we believe that it has to be revisited today? And why do we believe it can pan out today? So I'll give you a story from two directions. One is the push from technology at the bottom, let's say. At the bottom layers, we're having a lot of problems today. And there's a pull from applications and software at the top. So today we're having a lot of problems from the bottom as well as the top that is pushing us or kind of squeezing us to do in-memory computation, I would argue. So let me tell you the story of the technology side first. Why are we pushed from technology to have intelligent memory controllers that intelligently process the data. Why? Because our existing memory technologies are having a lot of difficulties today. DRAM, dynamic random access memory, is not scaling very well today, and I'm going to give you some examples of this. As a result, industry is finally examining controllers close to DRAM, and the industry is also open to new memory architectures. So these are some examples that were happening a few years ago. We have 3D stacked memories where logic layer has very high bandwidth and low latency access to memory layers, so we can take advantage of that for near memory computation. And there are other simple devices that people have put out where you can do processing in the row buffer, for example. And more recently, UpMem has produced a chip that can do processing, general purpose processing, near memory banks. And even more recently, Samsung has produced a more tailored processing in memory system where you can actually accelerate, multiply, and accumulate operations near memory banks as well. We're going to get back to these, but let me give you the story of why this is happening today. And the reason is memory scaling. Basically, we have a lot of issues with DRAM technology scaling. Memory scaling is not, well, at the bottom level at least. We have technology scaling is not going very well. And this is an old paper. If you're interested in some of the history of this, we have written this paper about 8 years ago or 9 years ago now that talks about why memory technology scaling is having problems today. So let me give you this reliability perspective. As the memory system scales, meaning as you increase the density of the memory chip, you reduce the size of the cell, and you put many more cells in a given millimeter square, for example. And because of this, memory is becoming much less reliable. This is data that we collected together with Facebook over the course of a year, more than a year actually. Basically, we looked at their data center. There are many data centers. There's a lot of data centers. So the confidence interval in this study is very high. And basically, the server failure rate correlates significantly with the chip density that's employed in the server. The denser chips lead to a higher server failure rate. Clearly, this is a correlational study. It's not causation. But we believe that there's a good link because the chips that are denser are having a lot more failures because there's a lot of noise that the smaller memory cells are subject to, and the memory cells are much closer to each other. So we're having a lot of reliability problems in terms of memory, and we need intelligent controllers to actually solve these reliability problems. And let me motivate us a little bit more. Basically, we built these FPGA-based infrastructures to understand the reliability, latency, scaling issues related to memory. You can read some of these papers. I'm going to mention some of them. And this is some of the like mid-level infrastructure. And we open source this infrastructure. So if people are doing FPGA-based studies to understand memory reliability, latency, et cetera issues, we actually support them. And you can find this paper as well as our source code online. And many people are actually using it both in industry and academia. But I would like to point out one interesting study that's actually a hallmark, in my opinion, of technology scaling problems that we're having with the main memory that we have today. And this is called the RowHammer problem. Essentially, today, at the software level, you can predictably induce errors in most DRAM memory chips. This is called the RowHammer problem, as I said. And more than 80% of the tested DRAM chips were vulnerable when we did the study early on in 2012 or so together with Intel. And this is really the first example of how a simple hardware failure mechanism, device-level failure mechanism, can create a widespread system security vulnerability. And as a result, people who normally deal with software are writing articles like this. Forget software. Hackers are exploiting physics. And this is actually a very good characterization, in my opinion, of a problem that looks like this. So what's the problem? Basically, it's a disturbance error. Whenever you read a memory cell, you're disturbing adjacent cells that you should not disturb. But it's happening today because cells are too close to each other and cells are too small. So in DRAM, if you want to access a memory cell, you need to open an entire row, activate an entire row, which means that you need to apply high voltage to that row. And if you want to open some other row, then you need to apply low voltage to this row, meaning pre-charge the array. And as a result, you can read another row. Now, if you keep doing this repeatedly, apply high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, or activate pre-charge, activate pre-charge, activate pre-charge to the same row, which is a valid action, perfectly valid action that a memory controller can do. And real workloads actually do that, as we will discuss in a little bit. It turns out in physically adjacent rows, you get bit flips today. Clearly, this is not supposed to happen because whenever you read a row, you should not disturb any value. Basically, you get data corruption in adjacent physical rows. And we call this the hammered row, we call this the victim rows. And we basically showed that more than 80% of the DRAM chips that are manufactured by the 3 major manufacturers in the world today are actually vulnerable to this problem because it's a technology scaling problem that was not anticipated well, let's say. And these are some data. Basically, you can see that all of the chips that we tested that were manufactured between 2012 and 2013 were actually exhibited this RowHammer problem. So let me quickly describe why this is happening. Essentially, there's electromagnetic coupling between the 2 rows. Whenever you activate one row, you also slightly activate adjacent rows. clearly there's a lot of low-level device-level explanation that I'm omitting over here. But at the abstraction level that I'm operating at, you're leaking data from some vulnerable adjacent cell little by little. And if you keep doing this hammering enough times, before the cells get refreshed, you leak enough charge from some vulnerable adjacent cells that you lose the data. So unfortunately, this is a reliability problem, but this is also a security problem, as we will discuss. Basically, a simple program can induce many errors. This is a program that we wrote and released at the time. A very simple, and it's a user-level program. What it does is it selects the address X and Y, and if the DRAM chip is, and it hammers them. And if the DRAM chip is vulnerable, you get errors. And we show that you could do this in Intel and AMD systems. Later works actually show that you could do this on any system with a reasonable memory controller. And this is a real reliability and security issue. It's a security issue because some malicious program can exploit these bit flips for malicious reasons. So basically, when we wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. I still believe that this is very fundamental. And we said that someone can take advantage of these bit flips that you're causing to take over your system. And later, Google Project Zero folks piggybacked on our paper, and they basically showed that problem. I'm not going to go over the details of this. This is actually very fascinating, in my opinion. This slide is copied and pasted from their blog post and Black Hat presentation that basically showed that they can gain kernel privileges with a user-led process by circumventing virtual memory protection. Basically, they do beautiful security engineering, and they induce these RowHammer bit flips. As a result, they were able to write to the page table of a user-level process, and they were able to modify the page table at the user level without actually causing any, let's say, detection by the system. So you can actually gain kernel-level privileges. Later research actually showed that you could actually do a lot of other things. This is work by TU Graz that show that they can gain unrestricted access to systems of website visitors by inducing these through the JavaScript. This is actually a very interesting work that showed that they could gain control of a smartphone deterministically by inducing these RowHammer bit flips in an Android phone. Other folks show that you could actually do this through a GPU in a much faster way. And you could actually do this through the remote direct memory access interface in a data center potentially, and take over a remote server. And I'm not going to go through this in detail. There are actually a lot of interesting attacks that people have developed. I will mention these recent attacks that talk about neural networks. So you may actually have very good neural networks. These neural networks may provide very good accuracy, but if someone actually takes advantage of bit flips like RowHammer, their accuracy can go down significantly, as you can see in this particular slide that I borrow from this paper. So basically, I think this sort of technology scaling issues are getting to the heart of what we really want to have from our systems. We want to have our systems intelligent, and we've built this machine learning infrastructures that are actually reasonably accurate, let's say, but can we trust them in the presence of these technology scaling problems that lead to bit flips? And these are clearly RowHammer bit flips, but there are other bit flips that may be happening due to retention errors, read errors, write errors, etc. I think we need to solve these problems related to these errors. Basically, memory scaling issues are real, and they're affecting our applications, in reliability of our applications, as well as security of our systems. The question is, what do we do about this? So clearly, I can talk more and more about RowHammer. This is actually a really interesting area. We wrote an invited retrospective paper on this. If you're interested, it covers a lot of issues from the entire system stack. But the solution to this, I believe, requires more intelligent controllers. Intelligence has to be added to the memory chips or the memory controllers. It doesn't matter where. And I think there are many, many proposals that are floating around right now. But we need to provide some security to fix these issues in a fundamental way. And that, I don't believe there's another solution to this, at least low-cost solution to this, without providing intelligent controllers. And this is one intelligent controller that we have designed and put out recently in the last HPCA. If you're interested, you can take a look at it. RowHammer has not gone away. So since it's a technology scaling problem, it's going to become worse and worse. And we have done a lot of analysis related to this. Basically, it's becoming much worse today. Number of hammers that you need to do to induce these bit flips is reduced, and existing mitigation mechanisms are not effective. Unfortunately, the intelligence that is being put into the DRAM chips is not enough. Basically, DRAM manufacturers said, we solved the problem, trust us. But they didn't disclose how they solved the problem. As a result, we took up the challenge, and in this paper, we demonstrated that you can reverse engineer what the DRAM manufacturers put into their chips, and it can basically induce RowHammer bit flips, even though the DRAM manufacturers claim their chips are RowHammer free. Basically, to solve this sort of issues, we really need to be, let's say, rigorous, and we cannot rely on security by obscurity. We really need to be open, and we really need to rely on security by proof, let's say. And basically, we've been doing a lot of studies on RowHammer more recently as well. The question is, can you actually identify chips that are vulnerable to RowHammer with good enough testing methodologies? Unfortunately, the jury is still out there, and we don't know how to do this yet. And there are a lot of papers that are being written on this topic that I'm not going to talk about. The most recent papers, as far as I know, are in Micro 2021. They go a little bit deeper into the analysis of RowHammer, into the sensitivities of RowHammer, for example, and they go a little bit deeper into what DRAM manufacturers do today and why it's not working. I believe there's more to come. I find this fascinating, and there's a lot of research in this area for those of you who are interested in doing research, and this is a good time to actually look into these sort of technology scaling issues. And I will finish this RowHammer part with detailed lectures. You can take a look at a lot of lectures. There's a lot of information out there that you can take a look. Let me actually give a high-level perspective on this, like intelligent memory controllers and RowHammer. We think of infrastructure as, we think of bridges as infrastructure, and humanity has been building bridges for thousands and thousands of years, right? Bridges are clearly critical infrastructures, and this is one example. This was the Galloping Gertie, which actually got destroyed like this because of a bit flip, let's say. You can read about it. And that's clearly a problem with infrastructure. Today, computing is a much bigger infrastructure than this. And we need to take computing much more seriously than we have been taking bridges so far, because computing is everywhere. Bridges are still small number compared to computing devices that we're going to rely our lives on. And this is another example of a bridge, let's say. If these people have a bit flip on this bridge, in the next second, they may not be very happy. So I believe security is about preventing unforeseen consequences going into the future. And we really need to develop techniques in our computing systems so that our computing systems are fundamentally secure, safe, and reliable. This example from Mr. Bean driving a self-driving car much before self-driving cars were popular is an example. Maybe this is a litmus test, right? Can we trust our computing system so much that we could drive it like Mr. Bean over here? So I think the part of the answer goes from intelligent memories. Basically, memory will have a lot of issues going into the future, but we need to design it to be intelligent. We need to design it to have controllers that can avoid these problems. And I think for this, we really need intelligent controllers. So that was an example from the push from technology. Basically, the technology is pushing us to have intelligent controllers that can basically understand what's going on in memory in the applications and to fix these reliability and security issues. I can give you another example from refresh, but we don't have time on this. Data retention is becoming much worse, for example. And all of the memory technologies that are interesting today are having these problems, not just DRAM. Clearly, DRAM is a huge market today. Almost all of the main memory in computing systems is DRAM. But even emerging technologies have this sort of issues. So that was a push from technology. Technology is pushing us to do something intelligent in our systems such that memory control should not be dumb anymore. It should be intelligent. It should be fixing these problems proactively. Let's take a look at the top of the computing stack. Systems and applications are telling us the same thing, perhaps even more strongly, let's say. Data access today is a major bottleneck. Energy consumption is a key limiter, and data moment energy dominates computation energy. I'm going to give you examples on each of these. But before that, the question, in my view, is actually much more pressing than what we have today with technology scaling. Do we want a world that looks like this, that we can live in, that we can actually leave it to future generations in a sustainable manner? Or do we actually want to pollute this world with the way we make our design decisions in our computing systems? Yes, computing system is not the only reason why we are having climate issues, but it's going to be a much bigger portion of the energy consumers in the world going into the future. So I would say that we would like all of them, meaning we would like high performance, energy efficiency, and sustainable at the same time. We cannot give up on high performance because we have a lot of problems to solve, but we want to get high performance with energy efficiency and sustainability. But the problem is we have a design decisions at the fundamental part of our computing systems that makes us go against all of these, basically. Our current design principles cause great energy waste because we're moving data all over the system. Data access is very costly today, from memory or storage or sensors to the computation units, but we're exercising it continuously, basically. We have to move the data before we can process it. Clearly, this is causing great energy waste. It's causing great performance loss also, because we know that data access is costly and we're moving the data in the first place. Okay, fine. We're designing our systems to actually avoid this performance loss. We're actually adding a lot of multi-threading capability, a lot of prefetching capability in software and hardware levels, a lot of out-of-order execution capability, a lot of caching, many levels of caching at many levels. Unfortunately, these are adding to the energy waste. So we're in a vicious cycle right now. Data access is causing energy waste. To overcome the performance loss, we're adding even more energy waste because this infrastructure, this hardware and software infrastructure that we built to tolerate memory accesses is actually not working today in many applications. today, if you really want to overcome the energy cost of data movement, you need to have a lot of locality in applications. And in many applications, we're not having that locality. In fact, many applications are increasingly random access, irregular. As a result, the locality is not being exploited. So all of that infrastructure that we have put in our systems is there, adding complexity and wasting energy. And if you want to solve this vicious cycle, we need to find the problem at the heart of the problem. Today, processing of data is performed far away from the data. And I think that's the main reason, the main thing we need to tackle. Basically, if you look at a computing system, I showed you this picture before, computing unit is heavily optimized, but everything else is not that optimized if you think about it. Well, clearly there's work in this area. I'm not saying that there's not a work in this area, but the amount of effort that we have put into the computing unit and the computing centricity of the systems is really hurting the overall system today. So yet we know that actually this is a problem. This is actually a person who has dedicated his life into designing compute-centric systems, Dick Seitz. Right now he's working on data centers, which is actually a different story. But Dick Seitz was the chief architect of alpha processors. His team designed the fastest alpha processor of its time, fastest processor of its time, actually. And after they designed this, he wrote a one-page article at Microprocessor Report, whose title is "It's the Memory Stupid." Basically, he said that we designed this processor. It's able to finish 4 instructions per cycle, but in real workloads, it's finishing 1 instruction every 4.7 cycles. Basically, it's operating at 5% of its efficiency. And he finishes the article by saying this: I expect that over the coming decades, memory subsystem design will be the only important design issue for microprocessors. And I agree with him. Fast forward 10 years, this is data from my own PhD thesis. We worked together with Intel, analyzed many applications. Basically, a state-of-the-art processor at the time was waiting for data most of its time. These are cache misses. If you're interested, you can read that paper also. Fast forward 10 years later, if you don't believe me or believe Dick Seitz, since everybody believes Google today, for good or bad, Google actually published a very nice paper in 2015 that shows that all of their interesting workloads, you can see some workloads that people may be using, search, Gmail, indexing, video, etc. They're all memory bound, basically. The processor is doing useful work only 10 to 20% of the time. Most of the time, the processor is waiting for data. And there's more analysis. So basically, we have a problem with processor-centric design today. We have grossly imbalanced systems. Processing is done only in one place, and everything else stores and moves data. As a result, data moves a lot. This is energy inefficient, low performance, and complex. And also, we have an overly complex and bloated processor, as well as accelerators. When I say processor, I would also mention that accelerators are very similar. So if you think about FPGAs, GPUs, or machine learning accelerators, they also need to get the data from processor and from the memory system. And they also have these complex hierarchies and mechanisms, which are energy inefficient, low performance, and complex. So as a result, we have this picture that I showed you earlier. Most of the system is dedicated to storing and moving data, yet still a system is bottlenecked by memory. Let me give you the energy perspective quickly. This is data that I borrow from Bill Daly. It's old data, but I think the conclusion is the same today. If you look at an arithmetic operation, is 20 picojoules in terms of energy. A memory read or write is 800x more costly. So if you look at the system design today, basically a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. The question is, of course, does it really make sense to bring the data and pay the energy cost of 2 to 3 orders of magnitude to do a very simple, energy simple operation? So I would argue that this is actually a great thing that enabled that has been enabled for us by technology scaling. If you look at this picture 70 or 80 years ago, when von Neumann was designing his architecture, for example, memory access was more costly than computation. Over the course of 70, 80 years, the same technology scaling that has been causing problems right now in terms of DRAM that we discussed has made computation a lot cheaper, but the interconnects and the memory did not scale. As a result, the picture has reversed significantly. So the design decisions that we made in 1940s, for example, when we were designing the first computers, don't hold because the energy cost of interconnect and memory system is much higher than energy cost of computation. So I believe we need to rethink. And if you actually do the calculations, to overcome the energy cost of this data access, you really need to have a whole lot of locality in your caches. And many workloads today do not have that sort of locality. Okay, so if there's a lot of other papers that are written that I'm not going to talk about over here. As a result, we have system level issues, like more than 60% of the total system energy is spent on data movement today. So I would argue that we do not want to move data. We want to be judicious in moving the data. We need a paradigm shift to enable computation with as much as possible minimal data movement. We want to be able to have the option to compute where the data resides. We don't want to do it all the time, perhaps, but we want to have the option to be able to compute everywhere. And we want to make the computing architectures more data-centric. So we need to have a paradigm shift. And memory is a good place to actually enable this paradigm shift. There's, of course, storage, which people are looking at. We're also looking at. I don't have time to talk about it. We need to process data inside the network, maybe inside the tape in other devices, inside the caches as well. Basically, we want to enable computation capability anywhere in the system as opposed to just the processor. Let's take a look at memory. Memory is very special, in my opinion, because today we have a lot of workloads that are designed for in-memory systems. For example, we have in-memory databases that fit the memory. You don't go to storage as much. We have in-memory graph processing engines. We have in-memory media processing engines, in-memory machine learning engines. These workloads are designed to avoid storage as much as possible. You don't always do it, of course, and you have sometimes one-time cost from the storage to memory, which is also important. I'm not going to ignore. I'm going to ignore that for now. But memory is special because we have these workloads that are in memory most of the time. But we cannot compute in memory. Basically, we would like to enable the processor to say, memory, can you do this computation for me? And the memory says, yes, and here's the result. And then the processor can do other things. We want to have memory as equals to the processor, if you will. We don't want to get rid of the processor. Processor-centric paradigm still has its benefits, but we want to partition the computation such that you can do the computation where it makes sense. Clearly, this opens up a lot of questions. I'm going to talk about several of these questions in the rest of the talk, but there are a lot of interesting questions, interesting research questions as well. How do you design the compute capable and the memory and the controllers? How do you design the processor core and in-memory units? How do you design software and hardware interfaces? Today, we don't have a lot of those. How do you design the system software compilers and languages to enable a computation paradigm like this? And how do you design the algorithms to fit the memory devices? As well as how do you revisit the theoretical foundations of computing? Basically, we need to revisit the entire stack of computing today. I say theoretical foundations, and I must actually mention this because we're talking about computer science here. Computer science is based on analysis of algorithms that actually count operations. So if you look at the big O notation, big theta notation, analysis of algorithms is really looking at operation counts, which really is processor-centric, compute-centric. The data-centric part of the paradigm is not there. So if you think about, if you want to design much more data-centric systems, maybe we should really look at algorithm design and algorithm theory of algorithms in terms of how much data movement they cause, how much memory space they lead to. So this sort of information is not there in the design of our algorithms. That's why I think this is a paradigm shift. We really need to rethink everything we're doing with computing today if you want to do processing inside memory in the best ways. Okay, in the rest of the talk, I'm going to give you some examples of this, but I'm not going to be able to go into a lot of detail. If you're interested in a lot of detail on this, we have written this long article that talks about an overview of processing in memory that gives you a historical perspective as well as the current perspective. And this talks about, you can see that we will talk about processing using memory, processing near memory, and we'll talk about adoption issues, which are also important, but we will not have time to go through everything in detail. But I will argue that today we need to think differently from the past approaches. And I think thinking differently leads to two different new approaches. One is processing using memory, the other is processing near memory. And these are two fundamentally different approaches. Processing using memory takes advantage of the underlying memory circuits and basically uses the operational characteristics of memory circuits to do computation. How can we think about the memory circuit and how can you take advantage of it to actually do computation and not just storage of data? And I think this is fascinating because all memory devices that we know of are capable of doing some amount of computation, the way we design them today. In fact, even off-the-shelf DRAM chips, you can take them and you can violate them some timing parameters, and you can actually mimic some of the operations that I'm going to describe to you in a little bit. You can do data copying, you can do data initialization, you can do simple bitwise AND and OR. This is fascinating because these memory chips are not designed for that purpose. They're designed for storage, but they can actually do computation. Now imagine what we can do if we actually go and design them specifically for both computation and storage. And I think that's going to change the paradigm. Processing near memory is more conventional, in my opinion. Today, memory is here, processor is here, they're far away from each other. And processing near memory says, okay, can we put the computation units closer and closer, 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 take advantage of some interesting technologies, if you will, such that at some point, memory and processing gets merged together, but they're different units still. And I think we need to look at both approaches. Now, let me give you the first approach in a little bit. First approach actually is significantly different because it will actually have significant impact on programming and algorithm design as well. The second approach, I think we can adapt our existing programming and algorithm design into the processing near memory paradigm. So there's more detail in the paper. Now let's jump into the first approach. So the idea of the processing using memory approach is, can we take advantage of the operational principles of memory to perform bulk data movement and computation in memory. We can exploit internal connectivity in the memory chips today to move data. We can exploit analog computation capability of the memory cells and the bit lines, etc. I'm going to give you examples of both. And I'm going to start simple, kind of cheat a little bit. Even data copy and initialization. These are actually important workloads. We do a lot of copying and initialization of our systems. Imagine you have a 1 terabyte database and you're initializing the memory. It takes a lot of time, actually. Imagine you fork a process, you initialize memory. Even if you do copy on write, it takes a lot of time, actually. And Google actually showed that in their data center workloads, data copy and initialization, these two function calls, only these two function calls occupy 5% of the cycles. So how do we do data copy today? Initialization is actually a special case of copy, so I'm not going to go into the details of initialization. But if you want to copy a simple small page, 4 kilobyte page in memory from here to here, today you have to go through the processor. You have no other option. You have to at least go through the memory controller. And this is the low, sorry, somehow I skipped. Basically, today you have to go through the processor. It's high latency, high bandwidth consumption, high energy consumption. But future systems should do better. Basically, in-memory copy in future systems should basically tell the memory do the copy internally and don't disturb anything else in the system. This way, we can have low latency because we're exploiting internal connectivity in the memory, and we're not exercising the long buses over here. No bandwidth utilization, no data bus utilization in the most important system resource that we have, the memory bus. No cache pollution, but you can eliminate that today with memory controller optimizations, DMA optimizations, for example, and no unwanted data movement. And I will show you that with a very simple modification to the DRAM system, you can get rid of a lot of latency and a lot of energy. You can reduce the latency by more than 10x, and you can reduce the energy by, let's say, close to two orders of magnitude today. And the idea is very simple. I'm not going to go into the details significantly, but any memory technology can actually enable this. In DRAM today, off-the-shelf DRAM chips can enable this by doing what I described by violating the timing parameters. But basically, if you want to do in DRAM row copy between two rows that share sense amplifiers in DRAM, you first activate the first row, which brings the data into the sense amplifiers. These already exist today. And then you first activate the destination row, which deactivates the source row and brings the data from the sense amplifiers to the destination row. So by using existing circuitry inside DRAM, the row buffer, the bit lines, sense amplifiers, you can do copy from one row to another row with minimal modifications if you want to do it completely reliable to the DRAM chip. So the idea is very simple, negligible hardware cost. And this leads to more than 10x reduction in latency and more than close to, let's say, 2 orders of magnitude if you optimize it, reduction in energy in terms of data copy. And ignore these bars over here because these bars actually enable data movement across different banks, across different subarrays, etc. I'm not going to go into the details, but these bars have reduced since this paper was published. They're close to the red bar. Basically, you can design the memory system such that it can do the data copy internally very efficiently with support from the memory chip. And I'm not going to go into the details, but this is one of the papers. And clearly, there are a lot of extensions that have happened, follow-up work. You can basically move data at smaller granularities. You can do faster inter-subarray copy, better interbank copy, etc. And I'm just going to show you some of the papers on this topic. And if you're interested, there are clearly lectures on this topic also. But let me talk about the mindset. Basically, this mindset says memory is actually good at doing data copy and initialization internally. So why don't we design it to do it really well? Have the specialized computation capability inside memory. And memory is an accelerator. We were used to building a lot of accelerators. They all have an Achilles heel. And that Achilles heel is the memory bus. Basically, the memory bus is limiting all of these accelerators. Why don't we design an accelerator over here that actually doesn't have that Achilles heel over here, which has low latency and high bandwidth access to memory, low energy access to memory. And memory can be actually programmed similar to a conventional accelerator this way also. Okay, maybe I cheated, if you will. That was the data copy initialization, but we can actually do truly in-memory computation as well. We can support in DRAM bitwise and or not and majority functions at low cost. And the idea is to use analog computation capability of DRAM. Activating multiple rows actually performs computation. I'm going to give you a little bit more detail in this. And you get, as a result, 30 to 60x performance energy improvement in bulk bitwise operations. And this paper details it significantly. And emerging memory technologies actually enable even more opportunities. They can do what we discuss in this paper, but they can do even more. They can, for example, do matrix vector multiplication in a crossbar array structure. And because they're not destructive, reads are not destructive, you can operate on data with minimal data movement in these technologies. Let me talk about DRAM. And this is, again, applicable to emerging memory technologies also. But if you look at 3 DRAM rows, 3 DRAM cells over here, you can do some fundamental operations by concurrently activating those 3 rows. And imagine that these are just 3 rows. Each can be 8 kilobyte wide. And you may actually have thousands of subarrays. So you may actually be doing this operation on more than 8 million, 10 million bits in a single DRAM chip. So the operation is triple row activation. You concurrently activate rows A, B, C. I'm showing 1 bit over here, and this is the bit line, which means that you connect the bit lines, the cells to the bit line, which means that based on fundamental circuit principles, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. This is a bitwise majority function. And you can actually design your algorithms to operate using bitwise majority. Now, this is not enough. You actually want an inversion function also. If you have bitwise majority plus an inverter, that's functionally complete. But you can also rewrite this Boolean equation. Set C to 1, you get the OR of A and B. Set C to 0, you get the AND of A and B. So basically, you can have a functionally complete Boolean Bach bitwise execution engine inside DRAM. And if you have a functionally complete engine, then the question becomes, how do you redesign your algorithms such that you can operate, you can express them in terms of these block bitwise operations? And that's essentially what we did in this work. Some of the algorithms, of course, are more amenable, or at least our thinking is more amenable today, because we have a lot of bitmap indices, bitweaving, database queries are doing, some of the databases are designed using these block bitwise operations. Web search similarly is designed using block bitwise operations, DNA sequence mapping, etc. But some of the algorithms we need to rethink so that we can take advantage of it. But let me give you an example from databases. If a database is designed to maximize block bitwise operations, and you map it to a substrate like Ambit, like we discussed earlier, you get more than 4 to 12x performance improvement in many queries. And performance improvements actually increase with the data set sizes that you have. I find this fascinating. Then the question becomes, how do you rewrite your algorithms, or how do you ease the programmer's job to enable a substrate like this, such that the programmer can actually take advantage of this massive bitwise parallelism that exists in your DRAM device? I'm going to talk about that in a little bit. But we've written papers on this topic. Clearly, you can take a look at them. This is one of the recent papers where we try to tackle the question, how do you ease the programmer's job? This was published in ASPOS. I'm not going to go into details. I'll give you some high-level ideas. Basically, it's an end-to-end processing using DRAM framework that provides a programming interface, ISA, and the hardware support, so that you can efficiently compute any complex operations. So you can imagine any complex operation, let's say convolution, and this convolution gets implemented by a design automation process that I will describe quickly in the next section. And the memory controller provides a convolution function internally using DRAM commands. And whenever the programmer uses a convolution function in the ISA, for example, it could be added, then this function gets invoked in the memory controller that basically sequences through a DRAM command, like triple over activation, like local operations that we discussed, so that that convolution function is actually efficiently implemented in memory. That's the idea. And arbitrary operations can be computed this way. And basically, we have minimal change to the DRAM architecture that I just discussed earlier. And this is a process, basically. Basically, user input, user has a desired operation. It can be expressed as a functionally Boolean complete circuit. And then we actually generate majority logic, majority and not. And this gets expressed in terms of DRAM commands. And now you have a microprogram that is part of the DRAM controller. And that microprogram gets called from the program using a special instruction that's added to the ISA. And that's the idea. Now, if you do this, actually clear some of the burden is reduced from the programmer now. The system has the burden, but the results are quite good as far as what, we're still working on, of course, to make it even better. But you can see that we can achieve more than the throughput of a CPU and a high-end GPU, as well as energy efficiency. And I think there's more work to be done to actually generalize this to many, many, many programs going into the future. So similar to this, actually, you can have physical unclonable functions. I don't have time to talk about this, but physical unclonable functions in DRAM. You can have a security infrastructure in the DRAM side, basically. You can have true random number generators on the DRAM side. And I don't have time to talk about this, but this is exploiting, again, the operational characteristics of memory to actually generate true random numbers. And if you want to execute, for example, a security critical application, you should really generate true random numbers on the DRAM side. And this is a paper that's coming up related to this topic. Okay, now with the given time, I will quickly talk about processing near memory and then talk about adoption issues. As I said, processing near memory is fundamentally different from processing using memory. It's similar to how we design systems today. So today we actually have graph processing workloads, and I'm going to talk about this from an application perspective. Graph processing is clearly very, very important in our lives. Many machine learning frameworks have it, many bioinformatics frameworks have it. Clearly, many social media and Wikipedia, for example, that many people are using is based on graph processing. Unfortunately, scalable graph processing is challenging. It's really a memory-bound problem. You can throw cores at the problem, but it's extremely inefficient to improve performance. Why? Because you have frequent random memory accesses and little amount of computation. So this is a great fit for processing near memory. Put the processors closer to memory, at some point immerse them with memory. And these processors do not move the data as much, but they move the instructions to the data. So we're talking about essentially a message passing system that I will describe. So a technology that enables this sort of approach is 3D stacking. You have a logic layer underneath memory layers, and logic layer can have many processors that can potentially be specialized for graph processing or machine learning or something else. So since this is actually a whole system design, I don't have time to go over the details of it. But basically in the logic layer, you can have a distributed system, which is programmed using message passing. And can basically lay out your graph nodes on top of it. And basically you don't move the graph nodes. Whenever you want to do an operation on a graph node, you send a message to the processor that hosts the graph node. You can see that these are all in order, simple in order cores. And these are programmed using message passing. It's essentially a distributed system in the logic layer. And then if you want to scale up the system clearly, you have many more of these cubes, if you will, logic plus memory chips interconnected with each other. And you can think of this as a primitive GPU today. If GPUs were like primitive in 20 years ago, this is a primitive GPU. It's a message passing based system, physically addressed. You offload your graph processing computation, and hopefully data doesn't move a lot in this system. And we actually ensure that data doesn't move a lot. I don't have time to go over this in detail, but proximity to data of the logic is what enables this system. Okay, and as a result, you get a lot of bandwidth. Basically, because your processors are tightly integrated with the memory, you get 8 terabytes per second bandwidth compared to all of the existing systems that we had at the time. Let me give you some promising results. So as a result, on 5 graph processing algorithms, you get more than 10x performance improvements. And again, this is data from 2015. Later works actually improved on our work. They did better load balancing in the system. They did better data mapping. They did better scheduling. They did better interrupt handling, etc. And as a result, today, actually, you can get close to 100x improvement on these 5 graph processing algorithms with the research that was done since then. I think this is significant. And energy reduction is also significant. We demonstrated more than 8x, but today we're actually close to 2 orders of magnitude if you specialize your system for graph processing. And if you're interested, this is the paper that originally introduced the idea. Now, let me quickly talk about more general purpose. So clearly, this is a specialized system, but can we actually do this in a general purpose manner? That's what we tried to do with Google in the work that I mentioned briefly. We wanted to look at consumer devices that are actually critical in terms of energy. And we wanted to look at these 4 popular consumer workloads in these devices. They're clearly Google workloads, but you have equivalents of these workloads from other companies. And we quantified the data energy cost of data movement. I mentioned that earlier. More than 60% of the entire system energy is spent on data movement. And we actually wanted to use processing in memory to reduce the data movement. But we want to do the function offloading. Basically, the programmer says this function should execute in memory. And we have the system infrastructure to support this. And how do you do this? Basically, if you want to be able to do this, the second observation helps a lot. A significant fraction of the data movement often comes from very simple functions in applications. And we design lightweight logic to implement these simple functions in memory. They can be implemented in small embedded low power cores or small fixed function accelerators or some FPGA-based reconfigurable logic. I believe actually a heterogeneous system design is useful for this. And as a result, we found out that you get significant performance energy improvements. It's not as impressive as 100x. It's more than 2x though. But the programming effort for this is much less, if you will. So if you're interested, there's a lot of workload analysis in the paper that I don't have time to go over. But for example, with TensorFlow inference engine, more than 50% of the inference energy is spent on data movement. And more than 50% of that data movement is coming from 2 simple functions that prepare data across layers, for example. And the paper has a lot more detail. So I can give you a lot of examples, but since we don't have time, I'm going to get toward the conclusion over here. But there's a lot of evidence that shows that if you do processing inside memory and near memory, you get a much more efficient system. And this is an example from GPUs. There are other examples from pointer chasing workloads that are actually difficult to do. The dependent cache misses, prefetching mechanisms, climate modeling. We can actually use FPGAs today to actually do better climate modeling near memory. Approximate string matching, time series analysis, neural network inference. This is a recent paper that we did with Google, but I don't have time to again go over this, but you can see that if you design data-centric accelerators for neural network inference, your performance energy can improve by more than 3x. And this is a heterogeneous accelerator that contains 3 accelerators. One is compute-centric, 2 of them are data-centric. Okay, as I mentioned, FPGAs are actually quite interesting to do near memory acceleration today as well. So these are all examples of revisiting the entire stack, but I believe these are also examples of getting there step-by-step with simple changes as opposed to changing everything that we have in our systems. And I think there are other simple changes that can happen with simple processing in memory with PIM-enabled instructions that I don't have time to go over, and this paper talks a lot more about them. Okay, let me give you some hope in terms of the industry. So when I was giving this talk, let's say 5 years ago or 6 years ago or 7 years ago, these this system didn't exist, for example. But now this system exists. This is a system that's designed by the UpMem startup in France, in Grenoble, that we're collaborating with. These folks, what they did was they basically took a DRAM chip, and each DRAM bank, they put a processor. And this processor is programmable. It's a general purpose processor. Now you can actually do a lot of offload a lot of applications to this processor. And these are real systems that we're working with. You can see a picture of a system that has more than 2,500 of these processors inside DRAM. And you can see that this is a simple processor over here that uses fine-grained multi-threading. You can actually run 16 threads inside this processor, etc. That I don't have details, that I don't have time to talk about the details. But we've written papers about this, and we actually released benchmark suites about this. If you're interested, you can find the benchmark suite, contribute to it, and these are some of the papers that talk about this system. So what we find is that these systems are very good at some workloads, but they're not very good at some other workloads, because some other workloads are extremely computation heavy, and we cannot put a lot of computation near the memory. Over time, this will evolve, of course. We can put more computation near memory, and these systems will become much more powerful. But today, these systems are not that powerful. So you need to make a decision as to what to offload to this system. And there are a lot of work that we have published that describes what you should offload and what you should not offload. Again, I'm going through this relatively quickly. And we have actually other work that talks about what you should offload and what you should not offload to the near data processing engines. We have characterized many applications for many distinct domains in this work, for example. And we categorize the memory bottlenecks in terms of whether you have the bottleneck in terms of bandwidth, latency, cache capacity, or your compute bound. You can use these tools to actually identify the bottlenecks in your application. And this can actually aid you to partition your application between the CPU, for example, and a near data processing engine like UpMem, for example. And this is all open source. Again, you can find information about it. There's a lot of research that can be done on top of it, in my opinion. And I would encourage the people to think about these research directions if they're interested. And one last thing that I will mention is Samsung, the biggest DRAM manufacturer, is finally pushing with processing in memory as well. Recently, they have announced in 2021 that they're putting functions inside each bank or next to each bank that can do computation, specifically machine learning type of computation. But over time, they have plans to generalize it. So this system basically has a small pipeline near. You can see the instruction set architecture over here, small pipeline that can execute this instruction set architecture, which is really tailored for multiply and accumulate and multiply and add operations, as you can see over here. But the important thing is this system exists, and people are actually doing experiments on it, and they're writing papers about it. So these systems are becoming real today, which is actually important. There are also other systems that I don't have time to talk about. These are some module-based processing systems. So I can go on and on about PIM, but I know we're already out of time. I will just mention that there are lectures, you can find information about it, and there are also tutorials on PIM that we have given that you can find online. So this concludes, I think, the major part of my talk. How do we design fundamentally energy-efficient architectures? I think the answer is data-centric. How do you design fundamentally high-performance architectures? I think the answer is, again, data-centric. And we really need to minimize the data moment in our systems. So clearly, these systems require a lot of adoption issues, and this slide lists a lot of the adoption issues. A lot of them are related to software. You can see it's about functionality and applications. It's about programming. It's about system and security support. It's about runtime and compilation systems to enable more effective integration with the system, as well as programmers, as well as system designers. It's about infrastructures to assess benefits and feasibility. I believe there's a lot to be done. We need to revisit the entire stack, but all can be solved with a change of mindset. And we need to change our mindset from processor-centric. We should not think about processor-centric. We should think about data-centric going into the future. And I think if we actually think that way, we can enable much more intelligent platforms, new medical and health platforms that can take advantage of systems that I showed earlier, and that can maybe revolutionize our lives. So as I expected, we won't have time for the next two parts. Data-driven, self-optimizing computing architectures are also important. They're part of the equation. Data-aware expressive computing architectures are also part of the equation, but we do not have time for that. But if you're interested, there's a lot more information on those in this tutorial that I gave in the International Electron Devices meeting a couple of years ago. Let me conclude. As I promised, I was going to talk about data-centric systems, but data-driven and data-aware are also important. But I believe it's time to design principled system architectures to solve the data handling problem. And we have a huge problem with data handling today. We want to design complete systems to be truly balanced, high performance, and energy efficient. And I think that requires us to think our systems and design our systems to be much more intelligent. And if you want intelligent systems, I believe they need to be data-centric, data-driven, and data-aware. And this requires us to enable computation capability inside and close to memory, as well as other parts of the system. I believe this can lead to orders of magnitude improvements, and I've given you some examples of this. Some of the examples were 2 orders of magnitude, for example, in terms of both performance and energy. It can enable new application and computing platforms. It can enable a better understanding of nature, because I think fundamentally nature is data-centric, data-driven, and data-aware. It's not processor-centric, and who knows what else. And I think to be able to do this, we need to have, in my opinion, better mindset about architectures, and maybe better questioning about what are we doing in our architectures? Are we really designing architectures that are truly intelligent? Or are we violating some fundamental principles that we're observing in nature that are enabling intelligence in humans? I'm not claiming humans are the most intelligent beings or anything, but clearly we're doing some things that are much better than computing today. But maybe not everything better than computing today, of course. But I think to get there, we need to revisit the entire stack. And we need to exploit good principles. There are many principles that I touched upon in this lecture. I didn't mention many of them. But more than anything else, I think we need open minds, meaning change our mindset such that we have a memory-centric mindset or data-centric mindset. And if you're interested in this, there's a short paper that I wrote, invited paper again in Date, that talk about these principles in a much more compact fashion. And I mentioned that there are a lot of things that we put out, but I think at this point, I'm going to acknowledge people who have supported this research. These slides will be available. I'm happy to send them to the organizers, but I'll acknowledge people who funded this research. This research would not have been possible with these people who fund the research. And I'll acknowledge more than anything else, my research group and collaborators, some of which are actually at NTUA right now, for enabling a lot of this research. And if you're more interested in our research, you can find some newsletters that we put out. And these are some interviews, etc., that you can find. And all of the things that we have put out that I mentioned are actually online. If you need something that's not online for some reason, please email us and we'll try to get to it as much as possible, as much as we can, actually. So thank you very much. And we're a big believer in open source. I must mention that before we conclude, actually. We put out a lot of things online, open source. So hopefully people in the world can do the research and can basically enable us to build much better, much more intelligent systems going into the future. So thank you very much. I'm a little bit over time. I understand that. I apologize, but I'm happy to take any questions, either online or offline at this point. Thank you.
Okay. Thank you, Onur. I do have time for a couple of questions, Harry?
Yes, sure, yes.
Okay. Anybody in the audience? Let me ask one question. So, Onur, I know the computation parts of this work. I follow it, obviously. A lot of acceleration is happening on the physical domain, actual memory, and all the rest of computer science is moving as far away from the hardware as possible, with things like starting from operating system and virtual memory, all the way to languages that are very, very, very high level. So how do you bridge the gap? How do we train people to do all these nice things they want to do in the high level, but also keep an eye on the efficiency of the low level?
Mm-hmm. Yeah, that's a great question, and it's probably a question that the real answer would lead to billions of dollars, let's say. but I think maybe there are multiple ways of thinking about this. One is, yes, it's true that a lot of computer science is moving away from the low level, and we have these very high level frameworks, and that's good. I think we would like to keep them as much as possible, but it's leading to a lot of inefficiency also. How do we get the efficiency? So also a lot of computer science is looking into these, I think, merging of hardware and software today. So if you look at companies like traditional companies like Google, Microsoft, Amazon, etc., they're all building their own chips. They're all building their own accelerators. So it's true that there's a push towards more efficiency, programmability in parts of them, but even the very traditional computer science powerhouses, let's say, they're also moving to this hardware-software co-design paradigm internally. Yes, maybe not all of their programmers are aware of this, but a good chunk of their programmers are actually trying to understand what's going on in hardware. I believe that this will continue. Maybe a bigger fraction actually will do hardware-software co-design, and people will actually figure out how to have many people looking at hardware and software, But I agree that we cannot expect this from the everyday programmer, like more than 90% of the programmers. The way I believe things will work out is for those, a good fraction of people, while I was at Microsoft, we used to call these people, let's say, Einsteins, geniuses. These are genius programmers. And there are some Elvises also who are quite good at programming, but the general programmers are not the best, let's say. These Einsteins and Elvises will actually provide the infrastructure that's extremely efficient and will enable these higher level programmers to actually take advantage of these hooks at the hardware level with the right interfaces. I don't believe we found the right interface. For example, I don't believe Python is the right interface to do efficient computation for machine learning, right? Everybody's moving away from Python. If you want to do extremely efficient training of data, you need to actually move it to lower levels and optimize it with the hardware software co-design. So as long as we find the efficient interfaces to call from Python, for example, or some other language, I'm not taking sides in languages over here, we can still maintain the programmability advantages at the high level, while also having a good base of, let's say, engineers and researchers who really understand what's going on. And again, I don't think we expect everyone to be able to do low-level optimizations. I think the answer is really from the interfaces side. People who know how programming, they should know what to express, but not necessarily how to take advantage of things underneath. Does that make sense?
Okay, yeah, thank you, thank you. Any other question? Let me check the chat here. I don't see something. Okay, then, Onur, many thanks. We have
I ask something, sorry, I had the mic closed.
Yes,
I'm not very familiar with this area. I'm mostly in the top, let's say, part of the algorithms, but I appreciate that work very much, and thank you for this stream of information. Great talk. I saw many improvements in the times X factors in several points of your work. Impressive improvements. I was wondering how well do these scale? Do they scale? Oh.
Thanks, Aris, for the question. So when you say scale with the data set sizes? Yes. So yes, basically they do scale. Of course, the limitation is, so what I have presented to you is mostly within a memory chip. And you can scale it by techniques that we currently use, like replication and having many memory chips, many processing units. So all of the understanding that we have developed in distributed systems, distributed algorithms can enable us to scale to many dimensions. Clearly, I don't believe that they will scale with a single memory chip. No question about that. A single memory chip is not enough for very large data set sizes. But I think we have a good idea of like distributed systems theory and algorithms today that can take advantage of the substrates that we discussed and amplify it to the higher levels. There's still some research that to be done in this area, I think. For example, scalability is limited by data movement across the chips and synchronization that you do across the chips. And I think there needs to be research in those, let's say, I call these pain points, synchronization and data movement across these massively parallel chips. But I believe those scalability issues can be solved over time as well.
Thank you very much once again.
Thank you.
Okay, then let's thank again Onur. Onur, I hope we see you in person soon in another one of these events.
Yeah, thank you very much, Dionysius. I hope in Samos as soon as possible.
Yes.
Yeah, take care. Thank you.
Thank you.